Hey there, in this video I want to talk about how things can go wrong using the Runge-Kutta method, and the good news that there are other routines that you can tell solve IVP to use that are usually more robust in those cases. The trade-off is that they're also slower. And well, just to show you what I'm talking about, if we look at our documentation here for solve IVP, we can see that one of these arguments is called method. By default, it says RK45, which stands for fourth order Runge-Kutta. The 5 there is because it's able to do some extrapolations and effectively make itself a fifth order method. And that goes along with having the adaptive step size. So it's by far the most popular ordinary differential equation solving routine, and it talks about it here. You have some other choices. There's RK23, which is a lower order Runge-Kutta, and I can't really think of a good reason you'd want to use that. Another one we're not going to use is LSOTA, which is the nice thing about LSOTA is it's sort of a one size fits all, but it's never like really greatest at anything. The other two I do want to talk about using is BDF, which is the backward differentiation formula, backward difference formula, depending on whose acronym you're looking at. We're going to learn about how that works when we learn about partial differential equations in a future video. But it's what's called an implicit method. So it involves a little bit of finagling the way the equation is written in the first place. The advantage there, though, is that this kind of method is really good for something called a stiff differential equation. And I'll show you an example of a stiff equation in just a moment. In the same kind of family as BDF, we have Radau. I'm not exactly sure how you'd pronounce that, which is kind of like an implicit Runge-Kutta method. And BDF is extremely well known, and since it is so well known, it's actually more popular than Radau, but in any testing I've done, Radau is actually going to be the better method. It's since it is based on a higher order technique, it tends to be more accurate with less points. And so, I mean, these are basically in the same kind of family, and we will learn how this works just in a future video. Okay, so let's look at the kind of systems that don't play nicely here with our Runge-Kutta. Our first example is going to be a spring, a damped spring. In particular, a highly damped spring. In particular, a highly damped, very stiff spring. And so what I mean by that is, let's write out our equation, but we're going to see that our coefficients in here are large. So remember, the order of our arguments here matters when we're using solve IVP. We want to unpack v and x. This is a second order differential equation. And we're going to make fx going to be v, so v will be velocity here. And then fv is going to be, let's make it negative 1001 times v, so this is the damping coefficient, depends on velocity, and then our spring constant will be 1000. Okay, so we have these two large-ish, pretty close to each other numbers. That's actually gives us kind of a lot of trouble numerically. And we're going to return fv and fx. That feels backwards to me. It doesn't really matter as long as we're consistent here for the beginning and the end, but I don't know. I want to do x first. Okay, anyway, so that's our equation. And so you remember the way this works. We have some solution object come out of this function here, integrate dot solve IVP. We give it our function. Let's go from t equals 0 to 1000. Having a big time value here makes things kind of bad for us. We will start with initial conditions of x equals 1, v equals 0. That should be fine. I don't want them both to be 0 because it doesn't move. And then here for method. Okay, this is kind of extraneous, but let's just by hand put in the default method, and we'll look at what happens if we try different things. So we'll do RK45, and now to make a plot, we'll get our time values out of here. We'll get our x and v out of solution.y, it's called, and then let's just plot what it gave us, just to make sure it makes sense. So if this is an extremely damped spring, so its motion should look linear. It should basically just be a straight line as it slowly returns to its equilibrium position. Okay, so let's see what happens when we run it. And run it. And run it. Okay, so this is taking a while. And that's what happens with stiff equations. They take a really long time to solve with Runge-Kutta methods, well, with adaptive Runge-Kutta methods, because there's going to be at least some region in here where you need incredibly tiny step size. So it's making very, very little progress in time as it's trying to solve this. It will, in principle, eventually solve it. Now, if you're saying, well, just don't use adaptive methods, that's possible, but then it'll have terrible accuracy in the region where you should have had tiny step size. So that's not really much of an improvement. Okay, there it is. So this one did eventually finish, and it did make a straight line, and it did do a good job, if good means accurate job, but it took a long time for what I wanted, and it used a huge number of points. You can tell because these little dots are all overlapping with each other. Okay, so let's take this very same code. I don't need to replace the F. We'll just take from this line on. Take the very same code, and let's change our method here. Let's do the backward difference formula and run that, and it's instantaneously done for us because this is in a family of solvers that works really well with stiff equations. You can see it didn't need nearly as many points, but still gave me a nice straight line. If I wanted intermediate points, remember we can always add an argument here saying I want those things. That's that T of L argument, and you can tell it what points you want to see. Another option in here is Radau, kind of in the same sort of family of implicit solvers. Also extremely fast, so you can see it used even less points to solve what we wanted. And so in the case where you have a stiff equation, this is where you want to use. Now, if you're saying, why don't I just always do this? Why isn't this the default? It's because it's slower point by point. So in a problem where Runge-Kutta would have worked better, this will also work, but it'll take you a lot longer. So let's look at an example, another sort of example where things can go wrong. Let's do the pendulum one more time. I think it's like the third time we've done our pendulum. But here I want to talk about the energy of our system, mechanical energy. So here I do need to make sure I keep some units for mg and L, the length of the pendulum. Let's say it's a 1 kilogram, 9.8, 1 meter. I mean, I'll still make these nice numbers, but I can't just ignore them. Okay, so I need a function here to represent my pendulum. So that'll be a function of t and r. And we want to unpack theta and omega out of r. I want f theta is by definition omega. F omega is going to be negative g on L times sine theta. So that's just your typical pendulum equation. And here we want to return f theta and f omega. Okay, and then we want our solution code. I mean, we can sort of copy and paste that from above. We're going to adjust some values here, though. 0 to 1,000, fine. That's fine. We'll start at pi on 2, so we'll pull this back at 90-degree angle. We'll start with 0 angular velocity. We'll let RK45 stay our method here for now. We'll get our t. We called our variables theta and omega, so we might as well use those names here. And then we can plot, well, I don't want to plot theta as a function of time. What I want to plot is the energy as a function of time. Because an issue with Runge-Kutta methods is that they are usually bad at conserving mechanical energy. At every step in the process, you have some amount of error, and the way these things tend to work out is the error always tends to be in the same direction in terms of the energy. So you'll see that your system always gains mechanical energy or always loses mechanical energy. What this would look like is the pendulum spontaneously speeding up on its own or seemingly stopping on its own without any damping being added to the code. It'll just on its own slow down. And of course that can be an issue. Let's say you're trying to use differential equations to model the orbit of planets in the solar system and you discover that all of the planets spontaneously spiral into the sun. That's not a real result. That is an effect of this numerical inaccuracy in your equation solver. So anyway, enough talking about that. Let's write down the energy of a pendulum. So that should be like mgh plus 1/2 mv squared. So mgh would be mgl times, be like 1 minus cos theta. And then we have our 1/2 mv squared, or we could write this as 1/2 I omega squared, which I guess makes more sense with the variables we have. So 1/2 moment of inertia of our pendulum is ml squared. Of course, L was 1. And then times omega squared. Okay, and that's just our mechanical energy. So plotting that and plotting t, I mean, this should be a horizontal line because this is a system that should conserve mechanical energy. Let's fix some y limits on this just so we don't let the graph scaling mislead us. So we're going to go from 0 to 10. In fact, the energy here should be 9.8, I think, everywhere. And just thinking in terms of what our initial height was and that we start at rest. So let's see, is it 9.8? Does it stay at 9.8? Looks like it starts at 9.8, and this particular pendulum has lost like 80% of its energy after 1,000 seconds, which is not really that realistic for this equation. Okay, so what do we do? Well, we could try one of our other methods. We could try like BDF. I guess that needs to be a capital F. You can see it's taking longer. These implicit methods, point by point, are slower methods. Runge-Kutta was close to instantaneous. Okay, we can see this one did better. It's still visibly losing energy, though. We could go higher order with a Radow method. And this is going to take a little while because it's a slow method, but it's a very accurate method. So you can see our energy here, at least on this scale, is flat. I'm sure if we zoomed in, we would still see some wiggles. No method is going to be 100% perfect with energy because it is inherently a numerical method. But anyway, our actual best way to solve this problem is not just changing methods, although that is a solution, but instead to change the tolerance. RTOL stands for relative tolerance, and unfortunately, despite this being an important parameter, it's not listed in the main list of parameters. It's like way down here in like other parameters. Here it is, down here. So we can optionally set what tolerance we want. Let's say I want 1 part in a million. And so that was pretty quick. I was using a Runge-Kutta method, which is a fast method, and just saying, be more accurate. And that will work for us as well. Now, I'm not saying that this is the solution to everything. But it's the kinds of things you try. It's changing the methods, changing the tolerance. You'll see as we start to back off the tolerance, we start to see a little bit of, there's like a little bit of slope here. So there's a lot of, not quite trial and error, but things you can try. And of course we can go, to crazy high accuracy, but in this particular problem, we don't gain very much for it. Still, it didn't take all that long because Runge-Kutta is such a nice fast method. Okay, so those are the kinds of things you need to watch out for when you are solving your differential equations.